So today we're going to talk about section 2.6 from your book on Euler's method. Euler's method is a method for approximating a solution to a first-order differential equation. So we're going to imagine a scenario where we don't necessarily care about the specific function that is an explicit or implicit solution to the differential equation, but rather we would like to try to estimate that solution at a variety of points. So this is a technique for doing just that. So recall from calculus that if y equals g of x is a function, and you're looking at the graph of this function, then the equation of the tangent line to this graph at the point x0, y0 is given by the formula y equals y naught plus g prime at x naught times x minus x naught. So this is just something that you used in Calc 1 when you were estimating a function by using the tangent line, so you needed to find this equation for the tangent line. And for an x value x1 near x naught, we can use the tangent line to approximate the value of g of x1 by plugging x1 into our equation of the tangent line. So g of x1 is approximately equal to y naught plus g prime of x naught times x1 minus x naught. So that's the differential approximation of g for values of x near x naught. So we're going to use exactly this idea, this formula, to develop the method of Euler for approximating solutions to a differential equation. So suppose we're considering a first-order initial value problem that looks like dy dx equals f of xy with the initial condition that y of x naught equals y naught, and suppose y equals g of x is the solution to this initial value problem, but it's unknown to us. So we don't know this solution. Okay, but since g prime of x equals dy dx, but from our differential equation here, we see that dy dx is the same as f of xy. So if we use the equation of the tangent line from the previous slide, that g of x1 is approximately y naught plus g prime of x naught times x1 minus x naught. If we use that here in this situation, we plug the fact that g prime of x is the same thing as f of xy into that, we obtain the following formula for the equation of the tangent line to the graph near at the point x naught, y naught. It's y equals y naught plus f of x naught comma y naught times x minus x naught, and this is because g prime of x naught is the same thing as f of x naught y naught from this equation right here. So if we look at a value of x1 near our value x naught, we get the approximation that g of x1 is approximately our value y naught plus f of x naught y naught times x1 minus x naught. And these are all quantities that we know. So we can estimate the value of our unknown solution function for a value of x near our initial value x naught. So what Euler's method does is it just repeatedly applies this tangent line approximation formula to estimate the value of the solution to the differential equation at several equally spaced points. So we're supposing that we have equally spaced x values. We have our initial value x naught, then we have a value x1, which is x naught plus h, x2 is x naught plus 2h, and so to get to the next x value, you just go over the same distance h each time. And so if y equals g of x is the solution to the initial value problem, our goal is to approximate the values g at the point x1, g at the point x2, etc. Notice we're not saying we're approximating g of x naught. The reason is because we know the value of g of x naught. It's given to us as part of our initial conditions. So we're given from the initial conditions that g of x naught is exactly equal to y naught, and then our estimation for g of xn, for where n is one of the points, one of the equally spaced x values, g of xn is approximately yn, where yn is given by the formula yn equals yn minus 1 plus our step size h times f evaluated at xn minus 1, yn minus 1. Those are the previous x and y values. So summing this all up then, Euler's method is used to approximate the solution y equals g of x to a given initial value problem, dy dx equals f of xy with the initial condition y of x naught equals y naught, and you want to approximate this function y equals g of x at the equally spaced x values, x naught, that's the initial value here that you're given, but then at the value x1, which is x naught plus h, x2, which is x naught plus 2h, etc., and you keep going for as long as you want, however far you want to approximate the solution. Okay, so Euler's method says that to approximate that unknown solution to the IVP, you use the formula, well, g is approximately equal to yn, where yn is given by yn equals yn minus 1 plus h times f of xn minus 1, yn minus 1. So we're going to do several examples of this in class. We're going to talk about how to compute this by hand by making tables, and then we're actually going to learn how to also compute this using Excel to make the computations much simpler, because if you're approximating and you're only doing, say, 3, 4, or 5 x values, it's not too bad to do by hand, but say you want to approximate your function at 100 x values, it's going to be very impractical to do that many computations by hand, and you can use a computer, Excel, in Excel to make those computations, complete those computations in just a few seconds. Additionally, in class, we'll talk about a second value for approximating solutions in a similar way, but this second value, called the Runge-Kutta method of order 4, is actually much more accurate than Euler's method, and its computations are essentially impossible to do by hand. They're so complicated that it would take a ridiculous amount of time just to do one round of the computations. So that completes this video, so we'll talk more about this in class and in the computer lab.